Hello everyone, welcome back to my YouTube channel, JM Lectures. JM stands for Just Mary, that would be me. We're going to be continuing with grade 12 physics Matric questions. We are on unit 6, magnetism. So without further ado, let's move on to the question. So question number 25 states that if a charged particle enters into a uniform magnetic field perpendicular to its direction, then what will happen? The choices are, choice A, it moves in an elliptical path, choice B, the radius of its path is proportional to the magnetic field strength, choice C, the period of the motion is inversely related to the magnetic field strength, and choice D, the charged particle will not be affected by the magnetic field. So this question has to do with an interesting concept, the relationship between electric particles and magnetic fields. So in this question, it states that a charge, let's represent it like so, a charged particle has a certain velocity. And let's denote this velocity with V and an arrow on top because it is a vector quantity, its direction matters. And this charged particle enters a magnetic field perpendicular to its direction. So let's say we have a north pole somewhere over here and a south pole over here, and we have a magnetic field like so. This magnetic field is denoted by a B, also has a direction, and it is also a vector quantity. A very interesting thing happens when a charged particle enters a magnetic field. A force is sensed by this charge. This force has a very specific formula. The force is equal to the quantity of the charge multiplied by the velocity the charge is traveling, cross product by the magnetic field strength. So in this case, the cross product will actually end up simply being the scalar product between the two, meaning that the force is equal to the charge multiplied by the velocity times the magnetic field. The reason that this is the case is because the velocity and the magnetic field are perpendicular to each other. The force, I should mention, is also a vector quantity, and the direction of this force is quite interesting. Using the right-hand rule, we've already established that the velocity, let's say, is in this direction, and it is perpendicular to the magnetic field, let's say, is in this direction. So this force will be perpendicular to both, like so. It's hard to see this in a two-dimensional plane, but all three vectors, are perpendicular to each other, like so. So using the right-hand rule, I'll bring the picture up here. This right-hand rule shows that the velocity, the magnetic field, and the force all act perpendicular to each other. Now, what does this say about the charged particle? Well, the charged particle will move. So choice D cannot be the answer. It will definitely be affected by a magnetic field. Charged particles are affected by a magnetic field with a force described by this formula here. Now, what kind of path or what kind of motion happens due to this force? Well, the motion is actually a circular motion. This force, caused by the presence of a charged particle, a magnetic field, causes a circular motion. This circular motion can be described as a centripetal motion, where the centripetal motion is due to a centripetal force. So you have your center, like so, and you have some radius, and this charged particle will move in this circular motion. Now, what is the force that causes this circular motion? Well, it is called the centripetal force. So this centripetal force is represented as also a vector quantity, the mass times the velocity squared divided by the radius of the circular motion. Now, it seems that we were talking about two different forces, but in fact, this force right here and this over here, these two forces are actually equal. So we can equate these two equations. We can equate these two in order to get another formula. So these two forces can be equated as QVB is equal to mv squared. So the radius can also be rewritten as r is equal to mv squared over qvb. We can cancel out one of the v's with one of the v's down here. And finally, we get that the radius is equal to mv over qb. This is a very important formula that relates the radius of the circular motion of a charged particle entering a magnetic field, how it's related to the magnetic field. a very important thing that you have to identify here is that the radius is proportional to the mass, and it's also proportional to the velocity. Also, the radius is inversely proportional to the charge and inversely proportional to the magnetic field. So if we look at choice B, it says that the radius of the path is proportional to the magnetic field strength. That is not true. We can see right here that the radius is in fact inversely proportional to the magnetic field strength. So choice B cannot be our answer. So there's now a bunch of quantities that we can identify because of this force caused by a particle entering magnetic field and the particle moving in a circular direction. In fact, that will also cancel out choice A as a possible answer because it's not an elliptical path, but rather a circular path that the particle takes. So some of these other quantities that I mentioned, let me scroll this down a bit, you can also find the period of the circular motion, meaning how long does it take for the particle to move in one circular motion. The period, which is represented by t, is equal to 2 pi m divided by qb. And we know that frequency is the inverse of period, correct? So frequency is just the inverse of this, and that would be qb over 2 pi m. You can even find the angular velocity, and the angular velocity is 2 pi multiplied by the frequency. So you could simplify this and get that the angular velocity is in fact equal to qb divided by m. So you can get a bunch of different relationships that define or describe the circular motion of a charged particle entering a magnetic field. So it's a very interesting concept, and it relates, again, electricity with magnetism, which are very, very closely related. So you can see here that, let's see, for time period, for example, the period is directly proportional to the mass, and it is inversely proportional to the charge and the magnetic field. In frequency, however, you have the opposite. You have the frequency is directly proportional to the charge and the magnetic field, but it is in fact inversely proportional to the mass. If we look at the question, we're actually more concerned with the time period. So we see that the time period is inversely proportional to the magnetic field, and that is in fact choice C. The period of the motion is inversely related to the magnetic field strength. And that's it for this question. Okay, moving on to the next question of magnetism. Question number 26 states that two parallel wires, each carrying 5 ampere current in the same direction, are separated by 2.5 centimeters. What is the magnitude of the force per unit length acting on the wires? Is the force attractive or is it repulsive? So again, we are talking about the relationship between electricity and magnetism. It's strange to think that wires carrying electricity or carrying current can act in an attractive or repulsive way, as if they are magnets. So first, let's draw out these two wires. These two wires can be drawn like so. We have one wire here, and we have another wire parallel to it. So these two wires are both, okay, it looks like one is thinner than the other, but assume that both are equal. So these two wires are both carrying a current, like so. Both have a current. Let's consider this I1 and this I2, and they are a certain distance apart. Let's consider this distance apart R. So the question is stating that what is the force of attraction or repulsion, whatever the force is, per unit length between these two wires. So there is a force that I1 exerts on I2, and there's a force that I2 exerts on I1. The formula for the force per unit length, we're using this specific formula, the force per unit length, because we're not given the length of the wires. We just know the current flowing through these wires, and we know that they're parallel, and we know what distance they are apart, but we're not given the length of the wires. In this case, we usually use this formula. The force per unit length of the wires that these two wires experience is given as the current in the first wire multiplied by the current in the second wire multiplied by the permeability of free space denoted by mu naught, which is a constant number, and this is divided by 2 pi r, r being the distance between these two wires. Now we can simply substitute the formulas. Let's first write down here we can write that we are given that the current in 1 is equal to the current in 2 is equal to 5 amps. And the distance between the two wires is 2.5 centimeters. In meters, this would be 2.5 times 10 to the power of minus 2 meters. So that's all we're given. Let's go back up here to the question. Let me shift this a bit so we can see it a bit clearly. Okay, so the force per unit length is equal to the current 1, which is 5 amps, times current 2, which is also 5 amps, and the permeability of free space is a constant given by 4 pi times 10 to the power of minus 7 newtons per ampere squared, and we divide this by 2 pi r, and r again is 2.5 times 10 to the power of minus 2 meters. So let us try to simplify this question. Let me change the color here, and we see that we have ampere squared. We can cancel both of the amperes. We have 2 pi and 4 pi. The 4 pi can become 2. What else do we have? We have 10 to the power of minus 2. This can change this to 10 to the power of minus 5 instead. So the force per unit length can be equal to, here we have 5 times 5 divided by 2.5. If you can't see that here, we have 5 times 5 divided by 2.5, that would be 25 divided by 2.5, and that would equal to 10. So we would have 10 times 2, we have the 2 right here, so that would be 20 multiplied by, we still have the 10 to the power of minus 5 Newton from up here, and Newton meter. And where did we get that meter? That meter is from down here. It's important to be able to get the correct units at the end because it should make sense. It actually is a good way to cross-check your work. And this is correct because what we're looking for is force per unit length, and the unit we got is Newton per meter, so that does make sense. We can actually further simplify this. Let's get rid of one of these zeros here and make this minus 4. So we get that the force per unit length is 2 times 10 to the power of minus 4 Newton per meter. Now, to the question with whether the forces are attractive or repulsive, well, think of it as the opposite of charged particles. Remember how in charged particles you have like charges repel and unlike charges attract? Well, in this case, wires that have currents flowing in the same direction actually attract each other, and wires that have currents flowing in the opposite direction repel each other. So in this case, the currents are flowing in the same direction, and we will have an attractive force between the two. So that will be our final answer. If we look at our choices, we see that that would be choice B, 2 times 10 to the power of minus 4 Newton per meter, and it is in fact an attractive force. And that's it.